Hi everyone. So welcome to this video. This supplementary video is basically about trying to find the shape of a drop when it's sitting on a plane. And this problem essentially, is quite important in general, as we had discussed in morning in the lecture, is that contact angle measurements are very crucial for determining the properties of a material. And this shape fitting can sometimes be very useful. Sometimes it's not very easy to see the interface at the end. So shape fitting can help us determine the contact angle or other properties of the system. And in fact, to measure the surface tension, typically a shape of the droplet is fitted on a pendant drop, which is a slightly different problem, but has a lot of similar features. So what we will basically focus in the class typically is, a velocity profile or a pressure balance and so on. But I wanted to make sure that you also get exposure on how to find the shape of an interface. And that is typically not something that is generally covered in detail in these courses. So I thought I'd make a supplementary video about this. And in addition, this will also help you solve your homework 3, problem 3, which is basically a very similar problem. And I do hope it will be helpful to see this video and also solve that problem. Okay, so what is the problem setup? It has been given that we have a static droplet sitting on a surface with contact angle theta. So you can see there's a contact angle theta here, here and here, contact angle theta. And what we have to find is to find the equation for the shape of the drop. So the drop can be thought of. So if I want to sketch this line, and this is a 2D problem, so there is some z as a function of x, right? So z, which is the dimension in the vertical direction, has a function of is a function of x, or z is equal to h of x, uh, and we want to find the shape of the drop. And when gravity is zero, we also want to show that the shape becomes circular in 2D. In 3D, it will become spherical. Okay. Now, to do this problem, typically what you do is you start with conservation equation. So we'll start with conservation equation. Conservation equation. Okay. And to do that, basically recall that what we have been discussing for pressure and velocity, our conservation equations are rho del v by del t plus v dot del v and is minus grad p plus mu del square v plus rho g. Okay. And we know that velocity is 0, and the other equation is continuity equation. And because velocity is 0, this all goes away. It's a static system. Or we simply get minus grad p plus rho g is 0. And we have seen this problem similar in buoyancy and all, that this is what you get as the conservation equation. Okay. And what we also know is that pressure, second is, let's just say gravity, sorry, is gravity here is minus GEZ. Okay, so this is, if you look from here, this is minus GEZ. So if you substitute this in the equation, essentially what you will get is minus dP by dz minus rho g is 0. Okay, or pressure is minus rho gz plus constant. Pressure is minus rho gz plus constant. Um, so this is basically our equation, and here the thing is that pressure is a variable. Pressure is varying with z, so depending on where I'm in the drop. So note that this equation is within the drop, right? So where I am here, the pressures will be different, and the higher my depth is, basically the lower my z is, the higher my pressure would be, because it's minus rho gz. So if g is 0, I'll have the highest pressure. If g is some value, I'll have the lowest pressure. Now, to finish the problem, we have to know the constant, which we do not know. Let's call this constant c. Let's call this constant c. We do not know this value. We do not know this value. So what we will do is, to do that, we will use the boundary condition. boundary conditions. And so if you recall from the lectures, we have discussed four kinds of boundary condition: tangential velocity, normal velocity. In this case, velocity is zero, so those don't matter. Then we had discussed normal balance and the normal stress balance and the tangential stress balance. The tangential stress balance doesn't matter because if you will see from the notes, it's dependent on tau or the shear stress tau, and the shear stress is zero because velocity is zero. So the only thing that matters here is the normal stress balance. So we'll focus only on normal stress balance. And let's call this normal vector like this: phase one, phase two. Phase one is the drop. So this is the drop, right? Drop. This is air. And we'll apply this balance at all points on the interface. Okay, so this is an interface. So all points on the interface, we'll apply this. Or we will say is P, the pressure in the liquid phase at the interface, P1 minus P2 plus 2H gamma is 0. Okay, this is our equation, right? So P2, which is the pressure in the air, is given to us as P naught. Okay? Pressure in the air is P naught, which is atmospheric pressure, simply. So we can say this is P naught. Pressure on the first uh, phase, which is P1 here, depends on the Z, right? So it depends on the Z, and Z is equal to H of X, which is basically what we want to find. H of X is something we do not know. So P is minus rho GZ. Rho GZ is H of X. H of X plus C minus P naught plus 2H gamma is 0. Okay. So essentially, let me write this equation a little bit more cleanly. So note that P1, so P1 is minus rho G H of X plus C. And C we still do not know. And note that I'm not doing anything fancy here. All I'm saying is that minus rho G X, Z is the pressure inside a drop. And when Z is equal to H of X, which is the shape of the drop, which I do not know, it is varying with X. At that, whenever we have the interface, that's where we want to apply the balance. So this is my balance, and then P2 is P naught. So that's what we get. So essentially, what we get is minus P2. Sorry, let's just write this down. Minus rho G H of X minus rho G H of X plus C minus P naught plus 2H gamma is equal to 0, or C plus 2H gamma is rho G H of X plus P naught. Okay, so this is our equation now. So this is our equation where we have some interfacial tension, where some curvature force, capillary pressure. So recall that this is known as capillary pressure. Capillary pressure. And this is basically saying that whenever I want to find um, uh, the shape, I need to solve this equation where I still do not know C, and I also still do not know what is 2H. So we do not know C, and we do not know 2H. So how would we solve this problem then? So typically to solve this problem, the easiest approach is to assume that the droplet has a shape of a sphere or something like that, or a circle in this case. But the main point here we want to show is that it can have a general shape. It can have a more general shape. So what we'll do is, to solve this problem, we'll basically define the curvature. And this is something we have not done in this class. So the third step here is to define curvature 2H in a little bit more general terms. And this is something, again, we have not discussed in class. So the definition of 2H curvature is actually gradient of normal vector, or sorry, divergence of normal vector. So note that curvature has the units of meter inverse, gradient has this operator has the units of meter inverse, and normal vector has no units. So that's why this is a units of a meter inverse, or 1 by distance. And normal vector is something which is basically pointing normal to the shape, right? So we have something just pointing normal to the shape here. And how do I find that normal vector? What we want to do is we want to substitute this 2h as a function of h of x. H of x is the shape of the system, which I do not know. And what I want to find is essentially find this as some sort of function of h of x, function of h of x. And to do that, basically what we will do is, this is something you may not know as comfortably. You write z is equal to h of x, which is the shape profile. So this is the shape profile, right? Z is equal to h of x. And the or you can write as z minus h of x is equal to 0, right? And the normal function is actually gradient of this z of minus h of x by the magnitude of the gradient of z of minus h of x, and this is to make it unit normal. Okay, and you may not be very familiar with this. That's completely fine. Just remember that whenever you have a shape of of a of a system, you can basically find the normal vector through this operation. Okay, you take, write everything in is equal to 0 in the form of is equal to 0, and then you take a gradient. Okay, and then divide by the magnitude. So the gradient operator, remember, is del by del x ex, and there is no y dimension here. Del by del z of ez, right? There is no y dimension here. So the gradient, if you will, basically if you substitute this, the value, this basically apply gradient on this, the normal vector will become uh, Ez minus dh by dx ex divided by 1 plus dh by dx whole square. Okay, so I'm taking the magnitude of the numerator in the denominator, because easy and ex, so you sum the squares and take a square root. That's the magnitude. And the numerator is basically taking the derivatives first with respect to x, which is y, which is minus dh by dx ex, and then with z it is only 1, which is easy. Okay, so if you do this, you get this n vector first, and then we have to take a divergence, or we have to do 2h is equal to del by del x ex del z plus del by del z ez dotted with uh, minus dh by dx ex by 1 plus dh by dx whole square, and then you will have basically plus plus ez by 1 plus dh by dx whole square. Okay, so take a divergence operator now. So this vectors, two vectors will become scalar. And I leave this up to you, and this is something you also have to do in the homework. Similar thing is what you will essentially get is minus d square h by dx square. I again invite you to try this yourself. This is not very complicated once you apply a product rule, and this is we get a very simple formula relatively after that, which is the definition of curvature in a 2D plane. So this is what you get as the curvature, and you can check the units. This also has the units of meter inverse, because d square h by dx square is 1 by distance, so it has also the units of meter inverse, and essentially get something in the denominator. Okay, so what was the point of this entire exercise is to show you that you can get a curvature. A small note here is that the sign of this curvature would be sometimes tricky. In this problem, it is okay to keep a minus sign. Uh, and I am not going to elaborate too much on this. Basically, in the homework, we ask you to show it as plus. You can just ignore the sign and say it's plus d square h by dx square. Uh, it basically, we can talk about this some offline, and I will be happy to share more details with you how to determine the sign. That is beyond the scope of this video and the course, and you are not expected to know that how to determine that sign. But for now, this is the sign you will stick with for this problem. Okay, in the homework, you say just you can just remove the sign. Essentially, it can have both plus and minus. In this problem, it is minus. In the homework problem, it is plus. Okay, so that's something I'm not elaborating on too much. But the main point was that the whole idea here was to find h of x, and basically we have been able to find 2h as a function of h of x. So now I can substitute back. So I can go and substitute back, right? So you can go and substitute back in the equation, or c plus 2h gamma was rho g h of x plus p naught, I guess. So this would essentially become c minus d square h by dx square times gamma by 1 plus dh by dx whole square power 3 by 2 is equal to rho g h of x plus p naught. Okay, so we get a differential equation in h of x, second order differential equation, which essentially we want to be able to solve. Okay, so to solve this, we need boundary condition, and note that we also do not know c yet. C is do not know the value of c. So I'll explain how. But to solve this, we can basically want a boundary conditions of h. So dh by dx at x is equal to 0 is 0, and I'll explain that in a minute. And the dh by dx at x is equal to L is minus tan of alpha, tan of theta rather. So here, if you go here, basically you can see that you can determine minus tan of theta here. And this is the slope because the angle is pi minus theta in the positive direction. So it's minus tan theta, or simply you can imagine that there's a negative slope. So it's minus tan of theta because theta is acute. So theta is tan theta is positive. So dh by dx is minus tan theta. And the slope here at the center is 0. Okay. So if you solve this problem, essentially you will get some equation for h of x. What you do not know is c, right? And typically the c will be determined through, let's say, a volume conservation or so on. So you can apply volume conservation to essentially solve this. So it becomes a little bit of a more complicated problem once you start going into determination of c. But the main idea here was that you can see that we have written down an equation for the shape of the drop. So essentially, we did not assume it's spherical. We did not assume any shape. We just found the equation for the shape of the drop. And to do so, what we did was initially we applied a hydrostatic balance, basically, which was grad p minus grad p plus rho g 0, or p is minus rho g z plus constant. And the constant we do not know. Then we said, we'll apply the boundary condition to find that constant. In this case, we had to apply, because there was a curved surface, we applied the normal stress balance, and we got an equation for in terms of capillary pressure. But then capillary pressure itself was not known because we did not know the curvature. And basically we found from first principles, by finding the normal balance and then taking the divergence of the normal, what that curvature was. If you will follow these steps, this is actually very similar to what you have to do in the homework. Slight geometric changes, slight surface is a vertical surface and so on. But it actually is quite similar. And then this is the shape of the system, and we can essentially find it if we kind of knew, if we knew what uh, if essentially we knew the volume, we could essentially find the whole equation shape of the drop. And people do that. You can numerically do it. We will not go into solving this equation. The idea was to show and expose you to this problem. Now the second portion is to show that it is actually a circular when g goes to 0. And this is again important because you may have heard this long back that drops are spherical because it minimizes the surface area and so on. And that's true, but you probably have never actually done it mathematically. And this is a 2D problem. In the 3D problem, this will actually become um, this will essentially will become uh, uh, spherical drop, so on. So let's assume g is 0. Assume g is equal to 0. Then what you get is c c. I'll just take the c. I'll just write this as c minus p naught is d by gamma is d square h by dx square by 1 plus dh by dx whole square by 3 by 2. Okay. So this is what we get. I'll just rearrange it. And why have I written it like this? Because this is a constant. So if the shape has to make sure that this is also a constant, right? If the shape has this property that the right hand side is constant, then we basically are able to satisfy the equation while also satisfying these boundary conditions. So you may even say, oh well, why can't it be a planar surface? If it's a planar surface, we'll still have a constant equal to 0, but then we will not be able to satisfy the boundary condition. We want to be able to satisfy both the boundary conditions and to have this to be true. And what I just will just give you this as a result, you should please try and do this yourself, is that if you write this as h of r sine alpha plus h naught, and what I'm doing here is I'm writing this as a function of, so this is the equation of a circle, okay? This is what you can basically find, that this becomes an equation of a circle, and what you will be able to, you can convince yourself that if you actually put this back here, what you will get is d square h by dx square plus 1 by dh by dx square whole square. And I'm not going through the math here because it's a bit cumbersome. But if you're interested, I do invite you to check it out, and I'm happy to share notes or derivation with you if you do end up trying this. Is that this will come out to be 1 by r. Will come out to be 1 by r. And essentially what you get is you get that this is constant and equal to 1 by radius of the curvature of the radius of the circle. Okay, so it is a constant, and it actually, if it is a circle, it is a constant, and it can basically prove to you mathematically that the equation is actually a circle, because that's the shape that can satisfy that the curvature is this right hand side is constant, this value is constant, and it can also satisfy the boundary condition. Okay, so I've skipped over some of the steps, but I hope this idea becomes clear. So I'll just quickly recap what we did here. So what we did was we started with the shape of the, we wanted to find the equation for the shape of the drop for a static fluid given a pressure outside and a gravity. And what we did was we did a hydrostatic balance, essentially saying grad p plus minus grad p plus rho g is 0, or which gave us as p is equal to minus rho g z plus constant, a constant we do not know. To do that, we applied the boundary conditions where the capillary pressure came in. The problem was that because we did not know uh, the capillary pressure, because we did not know the curvature, we basically found curvature from first principles by defining the surface z is equal to h of x, taking a normal, taking a divergence. Then we found the mean curvature from that definition, which gave us a differential equation with boundary conditions and with volume conservation, which we will be able to solve. And finally, if you assume gravity is 0 and substitute an equation of a circle for h of x, we can actually show that the curvature is constant, which is what we need for to satisfy the equation and boundary conditions. So your homework problem is very similar, and we will not discuss the shape of interfaces in detail in this course, but I really wanted to make sure that I'm able to give this resource to you, because I'm pretty sure some of you you will end up using instruments where there'll be a shape curved interface, and you will be fitting these shape profiles to get information like surface tension, information like contact angle, and so on. And so at least you know the theoretical background behind those things. And I hope this video was useful. Feel free to write to me if there are any questions. If you do end up trying the math steps, I'm happy to check your math and share the notes. And I look forward to seeing you in the next lecture. And see you. Bye bye.